going to hold it up in the air, but then I'm going to connect it to a rubber hose, and then over here I'll have a little nozzle, a little opening. And if you miss this idea that it's a fluid, you might say, okay, what would be the pressure of it shooting out sideways? You might say, oh, well, the water above it's not very much. But what I'm trying to point out here is this box next to it needs to push back with the same pressure. And so this box, even though it's not right under this column, actually has the same pressure as the box that is right underneath it. And if we continue that logic, even if we don't have water directly above it, the pressure in each of these boxes at that same depth would actually be the same value. And so something like this goes shooting out, and to figure out what its pressure would be, don't look at the height of the water column right here. You have to come all the way back and say this is the height of the water column. And again, that is something that would only happen if the molecules could move around and flow. If these were something that couldn't flow, maybe these were stacks of bricks, I think you would agree that if I just put one brick right here and another brick right here, even though I stack a bunch of bricks right here and I stack it up really high, these bricks do not push those bricks out sideways. They don't flow. But the water will flow. And so that's why I have this second experiment, is to convince you of the behavior of the fluid. It is how high is what we call the head of the water. It's not necessarily the water directly above it. So here's my little rubber hose. Here's my IV bottle. Let me just cap it for a second. But right there is the top of the water. And so if I then take this rubber hose and maybe I make the head of the water much higher than the opening, you can see it goes shooting out really far. There's a lot of pressure here. But if I lower the IV bottle, then the height of the water above the opening is less and less. And so the pressure, the force shooting it out, is less and less. And of course, if I get exactly the same height here, there is no increase in pressure. So it doesn't go shooting out. And so that's why these old school IV bottles would be put on a rack. And so, you know, somebody was laying in the hospital bed, the nurse would come in and put the IV bottle up on the rack, and that would give it pressure to go into the blood. And the nurse might come back and check an hour later and go, oh, you're not getting enough. And so they take the IV bottle and they lift it up to the next hook. It's going to get more pressure. And of course, a very dangerous accident is if when the IV bottle slips off the shelf and goes below the patient. Now the blood comes out of the patient and starts filling up the IV bottle. And so then you are draining the blood out of the patient. And hopefully that doesn't continue for too long. And it can't. It's got to fill up the bottle. But those older ones were one of the reasons why they, have gone to the new computer-controlled ones. And so if you've been in a hospital recently, you won't see those old school ones. So you still do, because they're pretty simple ones. But usually it's kind of nice to have a computer that actually pumps it in. That way the computer can measure exactly how much the patient is getting, and you know exactly the accuracy and the rate. But anyways, it fits really well here with this description of then what's going on here with the pressure. And so if I didn't say it enough, the pressure increases with depth. Oh, let me show you one more part of this experiment here, because it really kind of illustrates that same thing, and it's kind of neat to see here. But what if I had a column of water with a big diameter and another column of water with a smaller diameter? And I hope what you caught here is, notice the pressure has nothing to do with the diameter, the width of it. It's just the depth of it. Did you see that? Did you see how in this derivation the area canceled off? And so it doesn't matter whether I have an aquarium up here and I go down a couple of inches, or whether I have a whole lake here. I could do the same thing in Lake Michigan. And the surface area and the width of it is huge. That doesn't matter. If I go down the same depth, whether it's in this aquarium or in Lake Michigan, as long as, the density is the same. So this is freshwater and Lake Michigan is freshwater. So if I go down that same depth, I would have exactly the same increase in pressure. And what's really kind of interesting about that then is, if I were to connect these two together down here at the bottom, what would happen? And I want to emphasize then, if I kind of split it here, there would be a push from this side based upon its height. It has nothing to do with its width. There would be a push from this side, which again would be a pressure that has to do with the depth. It has nothing to do with the width. And the picture I've drawn, clearly this water is deeper than this water, so this pressure is greater than this pressure. And so what would happen if you hook them together is you would have a flow of water from this one to this one. But I want to emphasize, it is not because it is wider. It is only because it is deeper. You can see the same thing if I draw a second picture. What if my column of water that was narrow was the deep one, and my other column that is wider is the shallow one? Then again, when you look at the pressures fighting each other, this one would have a greater pressure and the water would flow that way. So again, it has to do with the force. It has to do with the pressure, and the pressure has to do with the depth of the water. It does not have anything to do with the width of it. So in this case, what's going to end up happening is water is going to flow this way, and of course this water level will go up. Let me maybe switch colors here. Maybe the water level will go up to here while this one comes down to here. But eventually they're going to be at the same level. And when they're at the same level, then the pressure pushing to the right is equal to the pressure pushing to the left, and there's no more flow. And so the water would move until they're at the same level. The same thing would happen here. That in this case, this would go down and this would go up, and then this one's kind of narrow, so this one might go down to here, while this one only goes up to here. But again, the water would flow until they're at the same level. And so that's the consequence of this flowing of our fluid. They would actually get at the same level. And that's the third little piece one I want to show you. It's these different vases that I mentioned in the last chapter. If you look closely at it, they're all at the same level. It doesn't matter what shape they are, whether they are fat or thin or kind of have a little bulb here or a corkscrew shape, they're at the same level. I could even tilt it, maybe right there. And you'll see again, they're at the same level. You could tilt it this way, and they'll flow around, same level. Of course, purpose of this is to hold it this way and to show you different size cross sections, different shapes, doesn't matter. They're going to be the same depth. That is what gives you the same pressure. It's the pressure that is pushing them back and forth. So it's not the volume of it, it is, and not the weight of it, but it is the pressure of it. Well, let me keep going here, because this little fact that the pressure is greater as we go deeper, added to the fact that the pressure goes in all directions, has some interesting consequences. Watch this. What would happen then if I take my aquarium and I put an object underwater? Now I'm just going to make a rectangular object or a cubic object. But when I actually demonstrate it, let me use this rock. And so I can redraw here. Let me go ahead and erase my first little writing on here. And I am going to put this rock on a scale so we can read the scale. And then I'm going to put the rock underwater. Let me hold off though on putting the rock underwater, because I want you then to realize that what we just said was that the water puts a force, a pressure on every part of this cube. See, does the water underneath push up on the cube? Absolutely. But also, does the water on the left push the cube to the right? Yes. Does the water on the right push the cube to the left? Yes. Does the water above the cube push it down? Yes. See, the pressure, as I was trying to say back here, is coming from these molecules. These molecules are bouncing around. And I started this conversation by saying, okay, I could calculate how much that is by looking at its weight, but I wanted to emphasize to you, because it's a fluid, that's again why this physics only works for the fluid, that it is pushing in all directions. These molecules, as they're busily pushing up, trying to hold up that big column of water, they also ricochet and they go sideways, and they also go down before they can bounce back up to hold it up. And so they push in all directions. And that results in an interesting consequence. Let's talk about it conceptually first, and then do the numbers. Check the sound again here, Ron. I think I bumped that again. All right, we're good? All right. So it's pushing in all directions. Let's just do left and right first. All right, so here's kind of the cross section. And so if I look over here to the left of the box, these molecules would be pushing it to the right. These molecules would also be pushing it to the right. And then these would also be pushing it to the right. However, remember we said that the pressure gets greater with depth? So I would say that these down here, and maybe I'll represent that with a longer arrowhead, then a medium-sized arrowhead, and then a short one. These are all pushing this box did I say that right? They're pushing it to the right. So the water molecules on the left are pushing it to the right. But these water molecules that are on to the right of the box are pushing the box to the left. And again, they get bigger as you get down. But conceptually, I hope you're seeing, wouldn't those be balanced? And so I would think that if I put something underwater, it's not going to have a net push left or right. They are balanced forces. This is Newton's first law, right? If we have the balanced forces, an object at rest will remain at rest. So I would suspect that when I lower this rock into this water here, even though there are some molecules pushing it one way, there's going to be an equal amount of molecules pushing the other way. And because of that, you might go, well, why even talk about that? That's been kind of boring. Nothing's going to happen. Okay, but I want to convince you nothing's going to happen left or right. But let's have this same conversation up and down. Okay, so the molecules on the top would be pushing down. And they're all at the same depth, so I'll represent that with 3 arrowheads pushing down on it, all the same length. And under the box, I would have molecules pushing up on the box. But here's what I want to emphasize. Yes, all the ones under the box are at the same depth, and so all the ones under the box are pushing with the same amount. But how do the ones under the box compare to the ones on top of the box? See, aren't the ones under the box a little deeper? Aren't they then at greater pressure, so they're pushing more? And so this is the surprising thing that I'm trying to get at. This is called Archimedes Principle. When I eventually finish this conversation, it's Archimedes who recognized that if you put something underwater here, there is going to be a net upward force on it. The left and right, no, it won't get pushed left or right. But it will get pushed upward. Now, let's not forget, and I'll draw this in different color, and maybe red so it stands out, that the object itself has weight. So I am not at all trying to say that this object will go up. What I am trying to say, though, is no matter what object I put underwater, there will be an upward force from the water. And if that upward force is more than the weight of the object, it will float. But if the weight of the object is more than it, it will sink. Oh, watch. Let's see if I can illustrate that in this experiment here. I think most of you know that if I take this rock on the end of the scale and I look at it, so it's reading about 17 newtons right now, we would conclude that the rock weighs 17 newtons. But watch this for a second. What if I take my hand and lift upward on the rock until the scale reads 10? Does the rock weigh less now? No, the rock doesn't weigh less. The scale reads less. This is no different than if you've ever gotten on a bathroom scale and you don't like the numbers, you decide to lean on the cabinet and push yourself up. That doesn't make you any lighter. Sure, it reads less on the scale, but it doesn't change your weight. And that's what I'm trying to say here. If I were to draw a picture of this, and I'll take us back a couple of chapters to our free body diagrams. If I were to take then this rock, and right above it I have a scale, and the scale really reads how much is pulling up, because the rock is being pulled down by its weight. And let me just say F for the force on the scale. I'll go F sub S. Because at first, when I was just holding it here, the object was stationary, the net force was 0. I would say, okay, so since it's stationary, the net force is 0. That means the force lifting it up from the scale minus the weight pulling it down, that's gravity, must be equal. And so that means the force from the scale is equal to the weight. And that's the way you're supposed to use a scale. You're supposed to use a scale so that the net force is 0, and the only forces on it are the weight and the scale. That's how you know then that the reading on the scale is equal to the weight. And in my case, I was getting 17 newtons, which makes me conclude that the weight of the rock is 17 newtons. However, if I put my hand underneath it, and so here's the rock, and so again, the weight is pulling it down, which we know is 17. And if my hand lifts up it, so I'll call it F sub h, the force from my hand, and then it's still hooked to the scale, which if you remember, I put my hand under it until the scale said 10. What I want you to get out of this is I am not changing the weight of the rock. I am changing the reading on the scale. And what this would say then is if I was putting my hand underneath it, but the rock was stationary, the net force would be 0. And so the forces lifted up would be my hand and the scale, and the force going down is the weight. My hand, I get the reading on the scale, I get the weight, this right here, moved to the other side, is really telling me that the only reason the scale reads different is because my hand is doing part of the work, if lifting it up. My hand is doing 7. And so my hand is lifting up with 7 newtons, and the scale is lifting up with 10 newtons. The two together add up to 17 because that's how much the rock weighs. And so let me just say it again. We did some problems like this way back in chapter 3 so that you would understand scales a little bit better. Scales don't automatically read weight. If you use them correctly, they read weight. This is doing a scale correctly. This is saying that the object is stationary and the only forces on it are weight and upward from the scale. And so it's reading a 17. But this is using this scale incorrectly. I do this. My hand is lifting up with 7. The scale is lifting up with 10. The weight of the rock is 17. You can't read the weight of the rock this way. Although it's kind of nice then, and this is what I want to use it for, is that I can then use a scale to then show if anything else is lifting up on it. You see, with nothing else lifting up on it, it should be a 17. If anything lifts up on it, it'll read less than 17. So let's come back to our fluid. And so if I start this up here, reading about 17, and I submerge it underwater, and I guess I put it too far for me to read, but I think it reads something close to 10. That would tell me that the water is lifting up with 7. Just like my hand was a moment ago. And that's what I want to convince you. I want to convince you conceptually and experimentally that it's these molecules, and it's a result of pressure being bigger the deeper you go, that results in a net upward push of the rock. And in this case, instead of my hand pushing up with 7, I hope you saw that the scale dropped down by 7, right? It went from 17 down to 10. It dropped by 7. That's because the water was pushing upward. And this is why the water pushed upward. The pressure at the bottom of the rock was greater than the pressure at the top of the rock. Oh, by the way, did you also notice that the rock did not move left or right? And that's what we said. We said that looking at this whole idea of pressure, when you put something underwater, there should be a upward force on it. Not a left to right. The left and right would balance off, and so there is no net left and right push from the water, but there is a push upward. Now, in this case it was 7. Now, it probably doesn't take much more than you to see the obvious, but if I completely let go of the string in the rock, and I'll just hold it here because I don't want to get the whole string wet, the rock will sink to the bottom. But let me emphasize, the water is still pushing up. Now, it's not pushing up enough to overcome the weight of the rock. So the rock still ends up sinking. That's why I tried to put the weight in this picture in red to say, just because something sinks doesn't mean the water isn't pushing up on it. All it means is that the push upward is not as much as the weight. And so all of this is to say that if I take an object and I put it in a fluid, there is going to be a net upward force. Let's call this the buoyant force. And you've probably experienced that yourself. If you've ever gone swimming or even in a bathtub, you will feel as if you weigh less. Because again, without the water lifting you up, right now when I stand here on the stage, I've got to push myself up and I got to support all of my weight. But if I get into a swimming pool and I wade in until the water's up to here, the water is going to do some lifting on me. And because of that, my legs don't have to push as much. Now, the total upward force needs to equal my weight in order to keep me up. But you see, some of that lifting up is coming from the water. It is what we call the buoyant force. And so this is a long way of trying to convince you that there is a buoyant force. And hopefully you see it. Hopefully you've also experienced it in your own life, just getting in some water. But again, even if you haven't, I hope you will see it, and I'll just kind of show it again here, that the water itself is supporting this rock. And in this case, I would say it's supporting it by about 7 newtons. Because again, we've got to pull up with 17 right now. And so the net upward push needs to be 17. And so with the rock submerged, the water is pushing up with 7. And of course, the scale is pushing up with 10. Until the total upward is 17. So I wanted you to see why we have a buoyant force, and I want to emphasize then that you put any object underwater, it has a buoyant force. That is the physical cause of the buoyant force. Now we should ask the following question. If that's the buoyant force, how would we be able to measure or calculate or figure out what that buoyant force is? And so here's where Archimedes' genius comes into play. Archimedes goes, how can we do that? You see, if we start here with the rock, we clearly see that there is an upward force. There is a buoyant force from the water, but ultimately the rock does sink. So I would say that the weight of the rock is more than the buoyant force. Okay. Maybe we'll try something else. And so Archimedes grabs a piece of brass and says, all right, let's try this with a piece of brass. And so we put a piece of brass in here. And I better not let it go. I think you probably know. I'll gently let it go to the bottom so I don't break anything. But again, it goes to the bottom. And so like the rock, I would say, yeah, the piece of brass is being lifted up, but obviously the weight of it is more. So it sinks. So maybe he looks for something else. And he grabs a piece of wood and submerges the piece of wood. And of course, if you let go of the piece of wood, you'll see something a little different. This time it goes, oh, to the top. Well, why is that? Well, I guess then when it was submerged down here, the water must have been pushing up. That's the buoyant force. I'll say it again. It has that buoyant force because the pressure underneath the wood is more than above it. Okay. But then we have the weight of the wood pushing down, but apparently the buoyant force is more than the weight of the wood, so it goes up. Okay. So maybe I'm getting closer to this question of what is this buoyant force? Clearly, the buoyant force is not enough to lift up rock or brass, but it is more than enough to lift up wood. So it's more than wood, but less than brass. What is it? Okay, let's keep thinking about that. And if you think this through for a while, you hopefully are getting to the point of, if I could find something that would not sink or float, that would be the magical key, right? You see, if this pressure difference between the bottom and the top is what's making it go up, that's the buoyant force, and what's making it go down is the weight, and if some things go down, like a rock and brass, and some things go up like wood, and maybe I should show a second one. How about styrofoam? Put the styrofoam under here. Yep. Oh, yep. Goes up. The magical step in Archimedes' mind here is that if I could find something that would just stay put, it wouldn't go up and it wouldn't go down. And so he keeps trying things. And eventually it dawns on him. And I'm hoping it's dawning on a couple of you. What could I put underwater that when I left it alone, it would not sink and would not float? What would it do? What would that be? Do you see it? And this is Archimedes' genius. He says, here it is, right here. It was right in front of me the whole time. If I put a box of water in water, what happens to that box? It doesn't sink. It doesn't float. And so, therefore, the buoyant force of that object must be equal to the weight of that same box made out of the fluid that it is surrounded by. Archimedes puts it in this terms. This is the grand step of Archimedes' principle, the first of the two big principles of fluids in this chapter. And so what we call here today is Archimedes' principle is Archimedes realized that the main object of interest is a box of water within water, or a box of petroleum within petroleum, or a box of air within air. Because Archimedes says then, and he phrases it in a very clever way, that the buoyant force is then equal to the weight, and be careful with these words, it's the weight of the displaced, and that's not a very common word, but let's talk about it, the displaced fluid. In other words, coming back to this picture, if this box wasn't here, what would have been here instead would have been water. And if it was made of water, that water would not have gone up or gone down. And so he concludes that the molecules around it lift it up with just the right amount. Nature lifts it up with just the right amount so that this buoyant force is equal to the weight of the fluid that would have been there had you not put the object there. And so if I come over here and look at this piece of wood, for example, here's this piece of wood. If I submerge the wood underwater, and if I put a little box so you can see it around this piece of wood, if this piece of wood was made out of water instead of wood, in other words, the fluid that would have been there. See, when I take this away, there's now water there. And so this right here is displacing the water. This is moving the water out of the way when I put it under here. But Archimedes is saying here that the molecules around on the outside are going to lift this piece of wood the same as if that same volume of wood was made out of water. And in this case, the piece of wood doesn't weigh as much as that same volume as water.